turkey because they don't eat it. And, oh, are these favorite or least favorite?
These are favorite things.
Okay, favorite, okay. And then grass. Okay. Stuffing, squash, and mashed potatoes. So, yeah, a very nice assortment of favorite dishes. In terms of an overview, the Unit 8 is in the Megadoc. The technical article for this will come out tomorrow, so anyone who's on the technical track, feel free to go over it. However, the homework for this week is fully optional. The synthesis questions are required, but the project and the technical article synthesis questions are fully optional because we understand it's finals week. So feel free to not do it or do it based on how much time you have. And if you guys have any questions on the technical article, feel free to direct that to your TAs or to Misha and I. I'd be very happy to help with it. And yeah, make sure for the certificate, we will be handing out the certificate next week on Friday, hopefully at the same time, and we will send a message with the place as well. So make sure that you guys finish all the units up until Unit 7 by next Tuesday, because on Wednesday we will be printing out the certificates. So if you guys have any units you've been running late on or you've been struggling to get in, this weekend is a perfect time, or this Monday and Tuesday, to get in those units so we can print out your certificate and hand them over to you. Okay, now for the attendance forms, if everyone wants to scan these QR codes and indicate that you were here.
Which one is for UW?
Not sure. Try scan.
And find out.
Yeah, scan and find out.
Non-UW is the one on the left.
Okay, non-UW is the one on the left. The UW one is the one on the right.
Am I wrong? Oh.
Yeah, let me know if I'm wrong. Okay, can we get a raise of hands if you guys have finished the attendance form? Okay. 2, I'll give it maybe 1 more minute. I also really appreciate all of you guys for coming here during Dead Week. I understand that you guys are probably busy with finals and everything, so I very much appreciate you guys coming and learning about language modeling for an hour. But yeah. Okay, so I think I will go ahead and get started. You guys can wrap up the forms, and I don't know if there's any issues with that, let me know, and I'll take care of it. Okay, so for our agenda today, we're going to be covering the introduction, so what is language modeling, some examples as well. We will be then covering some foundational concepts like tokenization and word embeddings. And then we'll go on to sequence modeling and talk about sequence predictions. So if you guys have words in a language model and you want to predict what words are coming next, how you can kind of do that. Then we'll be talking about some architectures of language modeling. So what are some frameworks that you can use to actually implement this in, and some applications of language modeling as well, and some advanced topics as well. So first, to start off with the introduction. So let's start off with an overview of what language modeling is and how it works. Language modeling is essentially the process of building computational systems that can understand, generate, and transform human language. This involves predicting the likelihood of the sequence of words or tokens, which forms the foundation for many powerful applications like text generation, translation, sentiment analysis, and conversational AI. At its core, language processes or models learn the patterns, grammar, or context from a lot of data, right? So by doing so, they produce text that is not only coherent, but it also is relevant within their context. It relies on statistical patterns in the data to predict the next word or token in the sequence. So in terms of some key features that are outlined on the slides here, language modeling can be broken down into 3 primary factors. The first one is prediction, right? So one of the most fundamental tasks to forecast the next word or token in a sequence is based on what has already been written. For example, in the technical article you'll see this, and also on the website you'll see this, but if I say the quick brown, the next word could be something like fox. So the second thing is patterns and context. These systems learn from large data sets, enabling them to understand the grammar, syntax, and even deeper meanings within a sentence or conversation. For example, they don't just predict words randomly, they analyze what is grammatically and contextually appropriate. Applications. The ability to predict and understand context allows for a wide variety of applications, including chatbots like ChatGPT, which can engage in natural conversations, search engines like Google, which provide relevant results to your queries, and also language translation tools like Google Translate that convert text across languages with a lot of remarkable fluency. So now on to our first question. So are there any examples of AI applications that involve language modeling, and what have you used? So please turn and talk to your neighbor for like 30 seconds, and then raise your hands if you guys have like a good result. And then yeah, let's have you turn and talk to, right?
Start matchmaking.
Oh yeah, Misha will start matchmaking all of you guys.
Unless you want to do it yourself.
Unless you guys want to do it yourself. So if we don't see you talking in the next 5 minutes, or sorry, 5 seconds, you will get matched. Okay, so you just talk to
I guess most recently, I always get the pop-ups, even though I disable it sometimes.
Hi, you two lovely people in front of me. You would like to come around this Aditya. Say hi. Wonderful, nice to meet you. Continue.
I'm Tamsin.
Oh, grammar. Oh, grammar. Yeah. So, because basically it's taking grammar and it's like looking at the features and like that. But the difference is it's still back.
Yeah.
Versus like
Anything with like predictive text, like that tries to figure out like what you're gonna say next.
that's like great ideas.
Yeah. Oh yeah, it does the like chat.
So Gmail. Wait, that's so good.
Yeah.
Yeah, and like even like the subject headers, you can auto like generate.
Yeah.
Subject header. It's really good.
Also like the predictive stuff where it tries to like guess what you're gonna say
No,
next.
that's a perfect example.
Yeah.
Talk about like how like when even when you're texting someone, you know, like how it will like fill in the word for you sometimes. Like that's a really big example of language modeling.
That's really funny because I talked about that in one of my other classes. It's a linguistics class. So that
Oh, so it's like relating language.
yeah, we had like a guest lecture from the language department, like computational. Yeah.
That's a good one. No, I think that was like apparently like a really big invention once they like figured out how to like finish words and like set text. I don't know, they were really excited about that.
Yeah.
So I was like, oh, that's cool. But yeah. Okay, keep discussing.
Okay, I've heard some amazing conversations. Can people bring up their examples that they've brought up so far? What are some examples of AI applications that involve language modeling that you guys have brought up in your groups? So, yeah, raise your hands if you have a good example. Okay, over there, example. Yeah, that's a really good example. Like, a lot of sequence modeling is looking at the future, so looking at based on your past data, what is the future words. But also a good example, which I heard a group over there also bring up, is stuff like Grammarly, which kind of look back at old words and checking like, you know, are those right or wrong. So yeah, any other examples? Let's get one more and then we'll move on. I heard so many good examples over here. One of you guys raise your hands.
Autocorrect.
Autocorrect, awesome. So when you guys are texting someone and like, you know how like in your text they'll like have like an autocorrect feature and they like correct your words? That's also a really good example of language modeling where it's looking at the letters together and seeing like what makes sense, what doesn't make sense. Okay, so moving on to the foundational concepts of language modeling. So the three main things we're going to be talking about here are tokenization, word embeddings, and an example. So tokenization is an essential first step in natural language processing. Unlike images and numbers, which you can feed into a machine learning model and it can just naturally translate over to the computer's process, text doesn't naturally translate over into your computer, right? Because your computer works with numbers, it works with binary. So if you just give it a bunch of words, it doesn't know how to work with it. So therefore, we have to convert this text into something that's called tokens, so your computer can understand those tokens. Tokenization solves this by breaking text into smaller, more bite-sized pieces that are digestible called tokens. So models like GPT and BERT only understand these numbers, so therefore this tokenization bridges that gap by transforming the raw text into numerical data. Without it, models wouldn't be able to analyze or generate language. And this process directly impacts the efficiency and the accuracy of these models as well. For example, subword tokenization helps a model recognize parts of rare words, so therefore it improves its ability to generalize and understand context. So tokenization is the first step, as I mentioned, in the NLP process where the text is broken into smaller and more manageable units. So depending on how the approach you take to tokenization is, this step can significantly impact how a model understands and processes language. Let's explore the main 3 types of tokenization shown here: word level, character level, and subword level. On the word level tokenization splits text into individual words, treating each word as a specific token. For example, the sentence "tokenization helps" becomes the tokens "tokenization" and "helps." Or the sentence like "Arya is the best teacher" would be "Arya is the best teacher," and each of those words is a token. It is simple, intuitive, and it works really well when the words are direct and straightforward. However, one drawback of it is that it struggles with complex words, because tokenization might not exist in the model's vocabulary. So if the model doesn't recognize the word, then it might be considered out of vocabulary and might limit the model's understanding. Then we have character level tokenization. This approach goes a step further by breaking each word into its individual characters. For instance, tokenization becomes the letters T-O-K-E-I-N, okay, whatever, the rest of the letters in tokenization. But basically, this fully avoids the out of vocabulary issue I mentioned earlier because each character is always recognized. Therefore, it is very useful for handling informal or creative language, like social media posts or words with unique spellings. On the flip side, this method generates much longer sequences, making it harder for models to grasp the overall meaning and structure of words. On the other hand, subword tokenization is a middle ground. It breaks words into meaningful parts or subgroups. For example, tokenization could be split into token and ization. Therefore, if the model doesn't know tokenization, but it knows what tokenization means, it is able to kind of balance the efficiency with the flexibility of that model. And this is widely used in modern NLP tools like ChatGPT and BERT because it is slightly more complex to implement, but it works a lot better than the other two. So therefore, this is probably the best approach as it gets the semantic understanding and it also works well in informal contexts. So let's walk through how tokenization leads to embeddings and dive deeper into what these numbers mean and how they're generated. So step 1, tokenization. First, let's take the sentence, "I love tennis," and let's break it into the tokens, "I love tennis." Each token represents a word or punctuation mark, which is then taken and processed by the model. But if the model doesn't understand it directly, it only works with numbers. That's where embeddings come in. After tokenization, each token is transformed into a vector of numbers that's called an embedding. For example, let's look at the word love, right? Love could be transformed into some like vector is basically just like a representation of a bunch of numbers. And it could be something like 0.59, 0.35, 0.75, and each number within that vector represents a different meaning, and the number within that vector represents how much it aligns with that meaning, right? So this vector might look random, but every number in this vector has a specific purpose for telling you what the meaning of that word is. And how are these numbers chosen? So, for example, for love, you could have one that could be how positive or negative that word is. So generally, love is a positive word, so it would rank pretty highly on that love dimension. However, you could have another dimension that says something like adore or enjoy, which might, or those are two other examples of words that might rank similarly to love in that vector space. So therefore, these numbers are learned during training, and the model is exposed to massive amounts of text, and through techniques like gradient descent, which we covered earlier, it adjusts the numbers in those vectors so that similar words end up with some similar embeddings. So therefore, if you look at the vector space of these embeddings, words with similar meanings will be mapped to similar places in this space because of the meanings of the word. So yeah, that makes these models really useful because it is able to kind of understand what these words mean instead of having something like saying that, oh, love just means 1, 2, 3, and just like put that into the model. It actually kind of understands what that word means in relation to other words based on the mappings of those vectors. So next question is, if you had to tokenize a sentence, what would you break it into? Words, characters, or subwords, and why? If people could just raise their hands to answer this, because I don't know if I have enough time for discussion. But yeah, there's like 6 different answers you guys could say to this, so nothing's wrong. I'll give you guys like 10 seconds to think about it. Oh yeah.
I was personally gonna say words because I mean I have the ability to like go to dictionary.com, and I think sometimes subwords can be confusing because like take the word genius and the word ingenious, and even though there's like the in prefix, it just still means genius.
Yeah.
Or like if you want to do like terrestrial or extraterrestrial, if you break it up into extra and terrestrial, like you might think, oh, more terrestrial, but combined it means outside of terrestrial. So I think like at least in like human language context, it's like, because English is so like messed up sometimes, it's like, sometimes the subwords lose context that the full words have.
Yeah, that's an excellent point. Yeah, and then you.
I was gonna say like the same thing because characters don't tell you much, and subwords, even if they're not used like exceptionally like rare cases, they're usually only you can only understand like meaning from them when they're connected to like the rest of the words. Like realization, it would only make sense if you have token. So it would kind of like a waste to have its own like vector because it wouldn't tell you much.
Yeah, okay, yeah, those are both like really good points. And also, like, one thing with you guys saying like words are better than characters, I think in the initial stages of some models that were kind of like ChatGPT when they were first making it, they were based on like generating the next letter. So because of that, like sometimes it would be like really good in the beginning, but then once like the model, I guess, like ran out of space or got tired, it would just start making like random garbage for like the rest of the sentence. And then that's why like those models didn't work that well, which is why like up until ChatGPT 3, basically all the earliest models were kind of like a toy because like they couldn't really actually understand the words that well. But if you use like newer models like ChatGPT 4.0, it has like a better understanding of like what does this word actually mean, and understanding is obviously like a hard word to use, but understanding as in it is able to map it and kind of contextually understand how these words are being used. So yeah, those are all great points. And I also wanted to use the strawberry example. If you guys ever hang out on like AI Reddit threads, you might have already heard about this. But basically, before when you used to ask ChatGPT how many R's are in a strawberry, it would very confidently tell you that the word strawberry had 2 R's. And you guys might be like, you know, this is kind of weird. And then I recently plugged this into ChatGPT just to like show you guys for this example. And it actually fixed itself in ChatGPT 4.0, where if you plug it in, it's now saying that the word strawberry contains 3 R's. So that shows how the language modeling is getting better. Yeah.
What if you give a blueberry?
Blueberry? Okay, yeah, I'll try that after. Yeah. But the reason actually for it being wrong with strawberry is because of tokenization. Because the starting word was strawberry, and the user asked the model to say, the user was me, and I asked it to say how many times does the letter R appear, and GPT processed the text by breaking the words into tokens. For example, strawberry might look like a vector with like 495, 675, and those are like the 2 things in the vector. And then because of that, since the AI didn't see the individual letters within the word and it was just breaking it into those tokens, it wasn't actually able to accurately count how many there were. But it looks like GPT 4.0 has better context awareness, and it might be using a hybrid approach, like it's taking token-based language modeling with enhanced like reasoning mechanisms. But also GPT is kind of like a black box because they don't want people to fully understand how it works, which makes sense. But yeah. So next, let's talk about word embeddings and their significance in understanding the relationships between words. So word embeddings are numerical representations of words that capture their meanings, relationships, and contextual nuances. So there are 2 primary types of embeddings. There are static embeddings and there are contextual embeddings. So static embeddings are things like word2vec, which is a natural language processing technique, but essentially it assigns a fixed vector to a word regardless of its context. For example, the word bank would have the exact same context as the word bank within the word riverbank, or a financial institution. So that's kind of what word2vec does. So it is good and easy to use because it's static. However, it could get confusing because if you're using the word bank, for example, it could think that it's like a financial bank when you're actually talking about like a bank that like an otter's like swimming in. On the other hand, contextual embeddings are used in models like BERT and GPT. And these provide word representations that adapt based on the surrounding words. So the word bank would have a different embedding based on its usage in the sentence. A really popular analogy for understanding contextual embeddings is this equation, which is king minus man plus woman equals queen, where basically you are saying that if you take the word embedding king and minus it by the word embedding man, you're getting some type of royalty thing that is not a man, and then you are adding in that it's a woman, and then you get a queen. So this kind of demonstrates how embeddings can model relationships, like genders or roles, in a meaningful way through vector operations. When thinking about embeddings, you can consider them as a way to map words into a high-dimensional space where similar words are closer together, like how dog and cat might be near each other, while dog and car would be further apart. So let's explore another embedding example. Imagine we are working with a word embedding model and we want to calculate what doctor minus hospital plus school equals. Take a moment to talk to your neighbors and think about what this would be. So doctor minus hospital plus school. I also generated like 5 possible answers to this, so there's no right answer. But are there any words that you guys think could kind of fit into something that is mapped to a doctor minus hospital plus school? And this could be anything, like the person's job. Oh yeah, awesome. PhD? Okay, yeah, awesome. So like doctor minus hospital, so doctor, and then plus school. Yeah, that's actually perfect. I think that's better than the ones I came up with. Yeah.
I just thought about teacher because it was just like somebody who works at a hospital and then somebody who works at a school.
Yeah, that's perfect. Teacher. Yeah. A med student? Oh yeah, that's really good. You guys are playing with really good ones. Wow. I came up with really basic ones. Okay, any other ideas for a doctor minus hospital plus school? Yeah. Researcher? Oh yeah, okay, awesome. Yeah, okay, all of those are really good things. So basically, this is kind of how the model would think about it, right? Is it takes like those meanings and it kind of subtracts it, adds it, and then it gets kind of a final vector. Because word embeddings provide a very natural foundation for modern language processing to allow these models to interpret and generate text that are accurate and relevant. So next discussion, I might skip this because of time. Now onto sequence modeling. So let's dive deeper into the process of sequence predictions and how models like GPT can generate text step by step. So starting out with the context, Aria, or actually never mind. So let's say we have the given input sequence, Aria is the best teacher. What's important here is that this isn't just a string of words or the model, it represents a series of tokens, each of which is mapped to a numerical vector. These vectors form the foundation for how the model processes and understands the sequence. By using this context, the model considers all the patterns it has learned from its training data. For example, it knows phrases like the best teacher are often followed by descriptors such as ever or explanations starting with because. But here's where it gets interesting. So for the probability section, instead of just guessing the next word, the model will generate a probability distribution over all the possible next words. So when you guys are texting someone, you guys might have seen that when you're texting, there's like 3 words that pop up that could be your potential next one. This is kind of similar to what's going on over here. But basically, if I give it something like Aria is the best teacher, the model might consider the likelihood of ever being the next word, like Aria is the best teacher ever. But it could also consider other options like Aria is the best teacher because XYZ or and XYZ. So those might have lower probability compared to ever because maybe the model has seen on its past data that ever is more likely to follow that sequence of words. But let's say that the model selects ever because it has the highest probability, like 60%. It doesn't stop there because then the model updates its context to being Aria is the best teacher ever, and that becomes the previous updated sequence. And with this updated sequence, the model will repeat the same process to predict the next word after that. So then it calculates another probability distribution, which might be Aria is the best teacher ever with a period, or because to expand it again, or and if it anticipates another clause. So this step-by-step process continues until the model is instructed to stop or produce a specific number of tokens. We can also break down the process of sequence prediction, focusing on autoregressive models like GPT. So what is an autoregressive model? An autoregressive model predicts text one word at a time. They don't try to generate the entire text in one go, but instead they build it up step by step. How do they work? They analyze the given context, which is our starting sequence, and then the model predicts the next word, which has the highest probability based on that context, and then after predicting a word, it updates the context by adding a new word to the sequence. This updated sequence becomes the input for predicting the next word. The iterative nature is what enables GPT to generate coherent, contextually aware text. So if we walk through the example, Aria is the best teacher, the model predicts ever as being the most probable next word, right? And then it predicts period, it predicts she, and then by the end of it, you would have Aria is the best teacher ever, she inspires, blah, blah, blah. So basically, this iterative nature is present in autoregressive models, and it ensures that every prediction reflects not only the immediate preceding word, but the entire context of what could come after that preceding word, and it allows the model to maintain fluency and coherence. So therefore, before, if you guys asked ChatGPT, hey, give me a Shakespearean play, maybe the first couple of things made sense, but then it didn't really match up with the second half of the sentence. This allows the entire sentence to kind of be in line with itself. So this ensures that the prediction is contextually aware. And you can also look at the temperature of the words as well. So one fascinating aspect of sequence prediction is how the model balances creativity and determinism. This is controlled by a parameter that's called temperature. So there's high temperature and there's low temperature. Low temperature is when the model becomes more deterministic, so it favors the more probable words. So therefore, if you had a model that was more low temperature, it might always select ever if you put it Aria as the best teacher. However, if you have a high temperature model, the model might allow for more creative and diverse outputs. So it might favor not always choosing the 60% more probable option, but maybe choosing the 40% or the 30%, just to make sure that every single time you generate a new sentence, it might be something that's different and more creative. And this is kind of why GPT can sometimes feel like it has kind of like a personality, because if you ask it the same question over and over again, it might give you a different response, just because it's not always going to give you the most probable outcome, but it might be balancing between a few other outcomes as well. So that's kind of like the magic of sequence prediction, is because it feels like it's more intelligent. So we are going to make this room a sequence prediction model. So basically, can someone give me an example sequence? So give me like a sentence, and everyone else is going to start predicting like the next most probable words. So let's start off with, someone give me like a random sentence. It can be like, I have 2 finals, or you can be more interesting than that. But yeah.
Hello world.
Hello world. Okay, awesome. So let's say hello world is our sequence that we're putting into this model, and then we want to have someone come up with the next word. So what is a good word that could come after hello world that makes sense in the context of that sentence?
Exclamation point.
Exclamation point. Awesome. So we could have hello world exclamation point. What do we think the probability of having an exclamation point would be? Someone give me a random number. 300? Oh, very high. Okay, 300. We could have, let's say it's like 85%. Okay, and then let's have another thing that could come after hello world. Maybe let's have like a word that continues the sentence. Hello world, mine. Okay, hello world, mine. Okay, awesome. So this is a really good example what's mine's probability?
20.
20. Okay, so let's say we have 85 and 20, right? So in our 2 high temperature and low temperature models, if we had a high temperature model, this would always predict maybe the 20, or it would predict the hello world exclamation point because it bounces between the 2. So you don't know if you're getting a hello world or hello world my, finishing the sentence. But in a more low temperature model, every single time you put in hello world, it's always just going to give you an exclamation point because it's like, it's probably going to be an exclamation point after that, right? And it's not creative or determined with it. So yeah. So what happens if a model predicts the wrong word early in a sequence, and how can that affect the output? I'll just take a hand for this one as well. Maybe someone in the back also. Yeah.
I guess like unless you have something balancing it out, it could end up derailing everything else.
Yeah. Unless you have something balancing it out, it could derail everything that comes after it. That's really true. Like if it says Aria is the best dancer instead of teacher, all the subsequent predictions could be really bad related to dancing, when Aria is not in fact the best dancer. Maybe Misha, but yeah. Okay, anyone else have a good response? I'll take one more and then I'll move on. Do you guys think the model could ever recover? I'm seeing some looks of nah coming from the corner over here. Okay, who thinks the model could recover? Wow, no one. Okay, who thinks the model can't recover? 3. Okay, a lot of people are not voting. Wow, people are very confused by this. Okay, yeah, so a lot of times like it could be hard for the model to recover if the context remains strong. For instance, like if the words are Arya is the best teacher or something in the classroom, then the model might realize that like the intended meaning is teaching, so it might course correct itself to making it from dancer to teacher. But otherwise, it could keep it as Arya is the best dancer in the classroom, right? So it depends on the nature of the model. Let's move on to architectures. So in terms of what you could implement this into, you could have it in a fast-forward network, a recurrent neural network, or a transformer. So let's talk about feed-forward neural networks and how they process data. So feed-forward neural networks are some of the simplest types of neural networks, but they're also very limited in specific ways. The ways that these work is that they predict the next token in a sequence by processing data in a single direction, from the input layer through the hidden layers to the output layer of the model. However, there are no loops or memory involved. This means that the model doesn't retain any information about the previous inputs once it's done processing them. This means that one of the key features of a feed-forward neural network is that there is a fixed input size. So therefore, they require all inputs to be of the same fixed size, which is called the context length. This creates challenges for variable length sequences, such as sentences of different lengths. How it works is that if the input is shorter than the required context length, then we use padding. If the input is longer than the context length, then we truncate it, which basically means that we cut it, wherever it's too long. Padding is needed because it ensures that the input to the network always has the correct shape. Let's take an example of, let's say that the context length is 6 and our input is I love learning AI. In this case, I love learning AI is 4 tokens, right? But we need it to be 6 tokens to put into the model. So we might have 2 paddings before, and then we say I love learning AI, so we have 6 tokens total, and we put those into the model. And in this case, I heard some of you guys saying you're taking CSE 351. This is kind of similar to in assembly, how you guys will have like zeros to represent padding. It's kind of similar to that in this feed-forward neural network. where basically it ensures that the network can process the input efficiently, but the padding tokens don't hold any meaningful data. They're placeholders, which means that the network has to be trained to ignore them during computation. On the flip side, if the input is too long, such as a long paragraph, it gets truncated, which means that we risk losing important information. Some of the limitations are that fixed input sizes means that it's not well suited for tasks with variable lengths of input data, such as text, where you might get more text over time. It's not going to take the context of that longer text, and it doesn't work well with that. And the other issue is that they don't have good memory, because they can't retain memory on previous tokens or learn relationships between tokens in a sequence. So maybe they learn relationships in the really, really short term, but long term, it can't remember anything that came before it, which makes it really unsuitable for tasks like language modeling, where context is essential to making a sentence that makes sense, But it does work really well for image classification or tasks where you're just giving it all the data at once and you're like, hey, use this, where the input size is fixed and the memory is not needed. However, for sequential tasks like text generation or translation like Google Translate, this does not work well at all. And then in terms of, I wanted to talk a little bit more about padding, because I was a little bit confused when I first heard about padding. But basically the reason why you need this again is that they cannot dynamically adjust their input size. And without uniform size, the computations involve these things called matrices, which you guys have seen a little bit over the last couple of weeks. But neural networks rely really heavily on matrix multiplications. So if the input sizes do not match, then these operations break down, which lead to errors in training or interference. Padding acts as a placeholder. And it also introduces no semantic value. Okay, let's take a closer look at how feed-forward neural networks process text using some simple examples. These demonstrate how the network handles sequences and predicts output step by step. For example, the quick brown fox. The network processes these tokens, analyzes the relationships between them, and then predicts the next token as jumps. Notice how the network doesn't remember the entire sentence. It only uses the fixed context window of the quick brown fox to make its next prediction. The second example is an apple a day keeps the doctor away. Here, the input is day, keeps, and doctor. Based on the context provided by the sequence, the network would predict the next word as away, because it doesn't know the full phrase, but it only uses the context of the tokens which it was given within that fixed context length. And the earlier parts of the sentence, like an apple a day, are out of scope because feed-forward neural networks lack the memory, right? And then the third example is ignorance is. And this is an interesting case because you're getting fed pad ignorance is. So the padding is used to align the sequence to the required length, which ensures that it fits the network's fixed input size. And even though pad has no meaning, the network processes the valid tokens and predicts bliss as the next word based on the phrase ignorance is bliss. So these examples highlight a few points about feed-forward networks, such as how they process sequences based on fixed context length, and also if important parts of the input are provided outside of the context, then they're ignored. Padding also ensures that these inputs fit the required size, but also adds complexity, as the network must ignore meaningless pad tokens, and these also don't have memory, as I stated again. Okay, here's a script to also explain the feed-forward networks diagram. So it kind of shows how if you start with the input phrase good luck with finals, and if you use word-based tokenization, where you split it into good luck with finals, and if you use token embeddings, then this would be a token embedding layer where it converts each token into a dense vector representation, which translates each word into a vector that the model can understand. And these embeddings capture the semantic meaning of each token. For example, good and luck would have embeddings that are closer together. And then they're passed through the feed-forward network, which is the core of the model, which is where these computations happen. And the network processes the embeddings and looks for patterns in the input context to predict what should come next. Remember, feed-forward networks operate on a fixed input window, so they don't retain any memory of tokens outside this context. Finally, the output from this network is passed on to the next token probabilities layer. This layer generates a probability distribution over all possible tokens in the vocabulary. For example, it might predict the next token with probabilities like you being 70%, everyone being 15%, always being 10%, and success being 5%. So yeah, I think hopefully you guys understand this. If you guys have any questions, raise your hands. But yeah, let's move on to recurrent neural networks. So these are slightly more complicated, but they're specifically designed for processing sequential data. Their key feature is the hidden state, which acts as a kind of memory. This hidden state allows the network to not only process the current input, but also retain information from earlier steps in the sequence. Let's break it down on how this works. So, at each step in a sequence, the network processes an input token. For example, a word in a sentence or a time step in a time series. It combines this input with a hidden step from the previous, with a hidden state from this previous step, updating the hidden state to represent its understanding of the sequence so far. This hidden state is passed forward time step by time step, allowing the network to retain context across the entire sequence. So why does this matter? Think of trying to understand the sentence, "The cat sat on the mat." By the time the network reaches mat, it needs to remember the earlier words like cat and sat to know that, okay, mat makes sense because it rhymes with cat and sat. The ability to keep track of earlier tokens makes these RNNs great for tasks like language modeling, where order and relationships between words are critical. Therefore, these are efficient with sequential data because they can handle sequences of variable lengths by processing tokens one at a time. They're also context aware because they can keep track of what's happened earlier in a sequence and captured relationships between dependencies between tokens and these relationships. And they're also very versatile across different domains because they can be used in terms of speech recognition, machine translation, sentiment analysis, and stock price prediction. But these aren't perfect either. One issue with RNNs is that they really struggle with long-term memory because they have difficulty remembering information from way far back in the sequence. So for example, if you have a really long paragraph, it'll remember the more recent sentences a lot better than it remembers sentences way in the past. And you guys might have noticed, like if you've ever used something like ChatGPT, if you guys have more recent messages, it'll like remember those, but if you tell it like, hey, like reference this thing I told you earlier in the chat, and if you sent that like 15 messages ago, it might not remember that as well as you've sent more recent messages. So that's one issue with RNNs. Another issue is unstable gradients, because during training, RNNs often suffer from vanishing gradients, which updates where the model kind of shrinks so much that it stops learning. And on the flip side, it could also experience exploding gradients, where the updates become so large that it destabilizes the entire training process. It's also inefficient for parallel processing because they process sequences step by step, so it can't process multiple things at the same time. It has to process everything in one go. So this makes them a lot slower compared to newer models. So to address these limitations, you guys could use something like LSTMs, which is long short-term memory, and GRUs, which are gated recurrent units, and transformers, which these are all in the technical articles, so you guys can read more about it there. Yes?
Can you expand on the gradients again?
Yeah. So the question was to expand on the gradients. So let me find it. Okay, yeah. So basically, the way that the thing about the gradients is that RNNs often so gradients are basically how these models like learn, right? So it's a lot of it is gradient descent, where it kind of goes to the bottom of the model and it learns. So one issue is because of the training of RNNs, sometimes it suffers from vanishing gradients, where like gradients farther off are vanishing. So basically it's updates to where the model kind of shrinks so much that it stops learning. So it's a little bit unstable with this, but transformations or transformers kind of help with this a little bit. And in terms of the hidden state, if you guys want to understand this better, the hidden state is the core mechanism that allows RNNs to retain information about past inputs in the sequence. So think of it as the model to memory, but basically what it does is it takes the current input token and the hidden state from the previous time step, and these two inputs are combined to update the hidden state using this mathematical function. And this matters because by repeatedly updating the hidden state, the network can capture information from the entire sequence. And looking at the differences between recurrent neural networks and feed-forward neural networks, do you guys have any differences that come to mind of when you would want to use one over the other? Or maybe I'll ask you guys. Okay, let's say you guys are taking in a bunch of pictures that are telling you to analyze whether someone has a tumor. Would you use a feed-forward neural network, or would you use a recurrent neural network? And keep in mind that they also want to optimize it for efficiency. Okay, raise your hands, feed forward. Raise your hands, a recurrent neural network. Okay, yeah, feed forward, because you're taking in that data in one go. And then let's say you guys have a model which wants to capture real-time text translation between someone who speaks maybe like, let's say, Aramaic and someone else who speaks Greek. So would you guys want to use a recurrent neural network, or would you guys want to use a feed-forward neural network? Raise your hands if you guys think you'd want to use a feed-forward neural network. Raise your hands if you think you'd want to use a recurrent neural network. Yeah, recurrent neural network, because you're taking in more data and the input data is of variable lengths. So perfect, you guys will understand. So yeah, you guys kind of understand like what types of tasks might RNN struggle with, what and why. Anyone have another response to this? What's another task that they could struggle with? Okay, I'll take one response. it could be like anything, like I said earlier, you guys could repeat the same stuff, but long paragraphs, or if you guys have like stock markets and stuff like that, let's say, and it's like, 15 years ago, some like really big stock pattern happened, the same stock pattern is happening right now. A human might be like, okay, like in 2008, like XYZ happened, so like we're seeing these signs, so the same thing's gonna happen again. But a model might forget that because that's like, oh, that was like XYZ years ago, and since it's so far back due to the vanishing gradient, an RNN might not remember that. So yeah, next thing is transformers. Haha. Okay, no one's laughing. Okay, let's move on. But basically, these transformers are a groundbreaking neural network architecture that changed the way that we process sequential data. Let's start with the basics. Transformers use self-attention mechanisms to process entire sequences at the same time, rather than one step at a time like RNNs. This key feature is called self-attention, which allows the model to focus on relationships between tokens, no matter how far apart they are in the sequence. Essentially, transformers replace the sequential processing that we were talking about earlier, where you can only process one thing at a time, by making it so you can process multiple things at the same time, making it more efficient. Now, why don't we just always use transformers all the time? Well, they're extremely computationally expensive. But some of the few major advantages of transformers are that it captures inter-token relationships extremely well. For example, in the phrase, "a quick brown fox jumps," the model doesn't just focus on adjacent words, but it also understands that fox relates to jumps, right? Because a fox can jump. This makes transformers ideal for tasks like language translation and text summarization, where context across the entire sequence is critical. It's also massively parallelizable, as I said, because transformers can process all tokens at the same time, simultaneously. And this is a huge advantage when working with large datasets, as it significantly reduces the training time. It also uses something that's called positional encoding, which keeps track of the order of tokens in the sequence. However, as I mentioned, they're computationally and data hungry, and it's also kind of like a black box because we don't fully understand how these transformers make decisions, so it's definitely harder to explain. So in terms of self-attention, what is self-attention? Why is it so cool? It's one of the core mechanisms in transformers. It allows the model to evaluate how every token in a sequence relates to all other tokens. This means that the model doesn't just look at the current token, but it also considers the entire context of the sentence. For example, in the sentence, "the cat sat on the mat," and it purred. The word "it" needs to focus on cat to understand what is purring, right? Self-attention enables this type of relationship building across the sequence. Let's break this into 3 main steps. Query. This represents the current token we're asking a question about. For example, if we're focusing on "it," the query represents "it." The next thing is the key, which is the representation of all the tokens in the sequence, which act as our potential answers. In our example, the keys would be like cat, sat, and "it." The next thing is value. This is the actual information associated with each token. For example, the value for cat would represent its meaning, like how we said a cat would be mapped similarly to a dog. And values are what get passed forward as context. And this is how self-actualization works mathematically. If you guys want to kind of understand how these keys, queries, and values work, but basically the query represents what we're looking for in the sequence, and that equation, like Q equals X times W subscript Q. This W subscript Q is basically a trainable weight matrix, which transforms the input embeddings into query vectors. Key encodes what each token contains that other tokens might find relevant. For example, the key for dog might encode that it's an animal or a subject. And mathematically, K equals X times W subscript K, where W subscript K is another trainable weight matrix for the key. So basically all these W's are just weight matrices for these values, and they're helping understand what those values are. And then in the third step, with the trainable weight matrices, these are basically just learnable parameters in these models, where these models adjust the matrices to optimize the relevance of these queries, keys, and values. And by applying these transformations, the input embedding is split into 3 rules that drive the self-attention mechanisms. Together, queries and keys, Q and K, determines the attention between tokens. For example, they help decide which other tokens are relevant to the current token. Values. Once the relevance is determined, the V vectors provide the actual information that is passed forward for future processing. So the main takeaway is that this diagram simplifies how the input embedding can be used to generate queries, keys, and values by applying different weight matrices. So turn and talk to your neighbors about this for like 1 minute, and then raise your hands. Actually talk. Misha, pair people up. Yeah. And pray out if you want to, but you're also free to keep sitting.
to be able to like understand multiple things at once. I just don't know like exact like
Conversing I hear is so great.
CSE magic behind the scenes that allows it to do that.
Yeah.
Oh my god, hi.
Oh my god, this is deep. Yes. Wow. Amazing, right? Friends. Okay. I'll leave now.
I'll give you guys like 30 more seconds,
There's like chairs right there.
maybe 15 more seconds.
Right next to the other people.
Okay. 5. Basically, I just had the guide to
So they're gonna
basically feel like someone's listening to your conversation and hopefully inspire you guys to give good answers. It was also in the slide deck, so I just figured I should keep in the guide. Yeah. I just put him in because I figured you guys could look at him while you're talking with each other. I don't know.
even though we had all the Thanksgiving break to do it.
He looks pretty solid, you know. He looks like a professor.
I just
Get you
got
guys in the
lazy.
mood to talk big professor thoughts. Okay. So basically,
Got really lazy.
we can do like a quick 5, 4, 3, 2, 1. People raise your hands. What's a good response? Something this professor would like listening to? Yes.
It's like RNs could only, RNs have a more limited memory, but transformers could take in, all the tokens and find relations between all the tokens at once.
Yeah, that's perfect. So transformers can take in all the tokens while RNNs have more limited memory. Yeah. Any other responses? I might move on just for time. Okay, I'm gonna quickly speed run this, applications of language models. Okay, let's take a look at the core applications of language models and how they're transforming the way that we interact with technology. First, let's talk about text generation, one of the most visible applications of language models. These models can generate coherent and contextually relevant text based on the input with which they're given. For example, writing assistants like ChatGPT or Jasper AI help users compose emails, articles, or even complex documents. They're also used for creative content generation, which is slightly unethically blah blah blah, but including like writing stories or making art and stuff like that, it could do that as well. Next is machine translation. Language models can automatically translate text from one language to another, making communication seamless across different languages. For example, if you are fluent in Aramaic and you are talking to someone in Greek, they will be able to understand you seamlessly with new technologies. Another major application is sentiment analysis, because this has applications in customer reviews. If you want to know if your customer reviews are generally positive or negative, you could take those embeddings and be like, hey, positive, or hey, negative. It also has social media monitoring or market research to understand like if someone's giving something that's problematic maybe, or to also understand public sentiment on a product, service, or trend. Next, auto-completion and predictive tasks. Language models play a big role in these types of tasks, like these tools predicting and suggesting the next word or phrase as you type, saving time and improving efficiency. For example, most of my emails have been run through a ChatGPT model to make sure that they are very fluent and all that. So things like Gmail Smart Compose, which can compose entire sentences, or GitHub Copilot can also help with text. I think one of you guys was also mentioning that Google Colab was helping you guys think of words to add to your code as well, so that's another example of this. Wow. Okay, personalized education. Oh, what are some ways that this thing is exciting? I'm just gonna quickly tell you guys. Personalized education can be cool, healthcare applications and all that. Okay, text generation. Some of the critical challenges and risks associated with text generation are ethical considerations. For example, they can be used to automatically generate fake reviews or manipulate customer opinions. Also, there's a lot of deepfakes and stuff like that that's circulating around, which could seem credible and also skew general opinion. There's also bias in generated content, like we talked about last week, how there could be gender stereotypes and stuff like that that is perpetuated through training data. And these models are learning based off of human data. Humans are biased. So therefore, you have to be really careful that your models aren't learning from human biases. And this poses a lot of risks. Like Amazon actually tried implementing their this like algorithm, which was like screening through resumes. And basically, they obviously told it like, hey, don't discriminate against women. But they found that like a lot of the old resumes, since most of the people who work there are guys, the model trained itself to penalize people if they had things like Women's Chess Club on their resume, because they were like, hey, if there's women in it, then they're less likely to be hired at Amazon. So if you had something like Girls Who Code or Women's Chess Club or something like that, your resume was actually penalized for it. So that's an example of why it's important. There's also the issue of copyright and ownership, like who owns the content generated by AI, but we talked about this stuff last week. We can also talk about hallucinations, like the more technical risks of text generation. AI hallucination happens when the model generates information that is entirely fabricated, but it sounds plausible. For example, the model might generate things like statistics, events, or quotes, and confidently present them to you and be like, hey, this is a fact, but a lot of times it isn't real. And these hallucinations happen because the models are designed to prioritize the fluency and coherence of their text and making sure that it sounds like something that could be said. However, they prioritize that over factual accuracy. And this has a real world impact because if these hallucinations occur in sensitive fields like law, medicine, or science, these could actually impact and have major consequences. For example, let's say a model misdiagnoses a patient by fabricating symptoms or treatments. It could lead to the doctor making harmful decisions. Therefore, one really cool thing that we should use, which I'm just going to skip over to this, is reinforcement learning with human feedback. And this helps address these challenges because while language models are powerful, they come with risks like biases, hallucinations, like we just talked about. But the way that reinforcement learning with human feedback helps this is through 3 steps. First, feedback. Human evaluators assess outputs generated by the model, which ranks them based on quality, accuracy, or ethical alignment. For example, when given multiple responses to a prompt, the human evaluators would choose the most helpful or the least biased ones. Next, this feedback is used to train a reward model, which is based on the AI, and the reward model assigns scores to the AI's outputs, rewarding desirable responses and discouraging harmful or low-quality ones. The final step is fine-tuning. The reward model is then used to adjust the AI's behavior through reinforcement learning, and this process helps the model produce better results for future prompts, ensuring alignment with human preferences and real-world standards. And this has been used in the real world to make sure that AI is being applied effectively, because we can't just send AI on its own, to do whatever it wants because of all these issues like hallucinations and biases, etc. So that's why it's so important to have human feedback in these reinforcement learning models to make sure that it works best. For example, imagine if there was a prompt like, what is the best political system? Without oversight, this model might generate biased or inflammatory responses, which could end up having really negative results. So therefore, with reinforcement learning with human feedback, human evaluators can train the system to produce balanced, neutral, and ethically responsible answers. So I'm going to move on to our Kahoot. Okay. Yay! Okay, and also